Alors, hop, ouf, share, tac. Okay.
Well, hello everybody. My name is Tilman Grünewald. I'm the head of the ESREF user organization. This is part of the ESREF webinar series that we've been organizing for you for the last 1.5 years. Today's guest is Jean-Sébastien MICHA from the French CRG Beamline BM32, a beamline that is looking at interfaces, surfaces, and material sciences. I had for myself the pleasure to work at this beamline 10 years ago with what I can only describe very invasive experiments, basically bringing my own detector. But I hope not everything is as invasive than this.
Et là, quand tu fais share, tu veux chercher.
I guess we would be ready for your talk, Jean-Sébastien, if you want to start.
Yes, thank you.
Just one thing. If you have questions from the audience, please put them into the Q&A box so I can read them out afterwards. Thank you, and yeah, let's enjoy the talk.
Yeah, thank you very much, Tilman. Thank you for this introduction. So I had also a good pleasure to work with you. And so it's also a pleasure for me to present what we can do with this beamline, quite an old beamline, maybe one of the oldest beamline at ESRF, since we have done many upgrades. And then I'm talking about maybe the last 5 years of activities of the beamline. So the beamline is still obviously devoted for the studies of using X-ray scattering of X-rays, and we are and the scope of this beamline is to address some issues, some studies in material science and nanoscience. So we are a team made by people coming from CEA, which is in Grenoble, and also people from CNRS. So this beamline, BM32, is a collaborative research group beamline. So it's not a public beamline. So people are paid by the French government, let's say, and instrumentation are also paid by the French money, and typical and contracts made in this framework. Okay, so we are quite many people to help the community to use the X-rays to investigate, to probe, to explore the materials, and in order to extract quantitative data on the materials. So the idea now, okay, so we are located at ESRF, obviously, and we are working quite a lot, and we have 2 ways to have beam time on the because we are a CRG beamline. So 1/3 of the beam time is selected by the ESRF committees, and 2/3 of the beam time is selected by the French committees. So actually, this is a common committees with the Soleil, the French synchrotron Soleil in Paris. So what is the specificity of the beamline? That we are a kind of platform. So clearly, we have a mission of services to the French and also international scientific community. And the idea is our ambitions are to facilitate the access of synchrotron techniques to the users. And we are also making a lot of instrumentation developments. And clearly, our mission is to support and assist the best we can the users. So clearly, there are several steps when you are using ESRF for your proposal and performing experiments. So, but we intervene in several steps. So we help the users before the experiment to design the experiment, to design the best way to collect the data, or the best system, the best model, the best geometry, the best sample environment, and so on. And we assist also the users during the acquisition of the data. And the idea is to produce, to collect usable data. And the idea, and then we are also assisting the users to for the data reduction that really can depend on the materials and the techniques we are using. And clearly, we are also assisting for the analysis and also for the interpretation. So we are Beamline, which is devoted to the studies of surfaces and interfaces. So, and we are using the scattering of X-rays to deduce, to extract information from structural properties of the materials. So 3 instruments for that. So the Beamline has got 3 experimental hatches, and you have to decide beforehand which instrument you want to use when you are applying for a proposal on the Beamline. And clearly the common things are that we are getting information about the atomic structure of the materials, morphology of the particles which are on the surface or buried inside the surface and buried into the surface. And we are also looking at the microstructure, and we are able also to look at the nanostructure and micro objects. So the idea is to obtain information on the structural parameters that describe the materials, and at the end, for the researchers, the idea is to correlate or to understand better what are the physical and mechanical and physical chemistry parameters, so that rule the properties of the thing. So 3 instrumentation, and going from the ultra high vacuum up to the air, or maybe a little bit of pressure. So, and you can also apply it so for different techniques, for different experimental conditions. We are able to do some in situ or operando measurements. So by varying the temperature, the mechanical stress, or we can also apply the current, electrical current or voltage, and we can also get the light emitted by the sample. So I'm talking about that a little bit later. So the main techniques that we are using, so this is what we are calling surface diffraction. So it's not as simple as putting a powder at the center of the diffractometer. So to perform the surface diffraction, you have to look in a specific way, and then this is called. So this is a little bit more complex than making powder diffraction. So this is surface diffraction. I'm going to talk about that. We are able to do some wide and small angle scattering, and since we want to be sensitive to the surface, it's better to enhance the signal coming from the interface and then from the surface, and then we need to illuminate the sample with the grazing incidence. This is what I'm calling the grazing incidence wide angle X-ray scattering, or the grazing incidence small angle X-ray scattering. So you can do this. There are also the possibility to change the energy of the monochromatic beam in order to enhance the signal coming from a specific element in your materials. And also what we are doing a lot is the X-ray reflectivity of the X-rays. So these 2 instruments are able to perform such kind of experiments. So either in ultra high vacuum conditions, so to follow the growth of heterostructure of nanoparticles and so on, of thin films and 2D materials, for instance. And or you can use this goniometer, which is a multi-purpose goniometer, and working at air, but you can put a lot of your own sample environment, provided that it can be fitted in this goniometer. And then the 3rd instrument is devoted to use, which is not so common in the community, is to use the polychromatic beam. So in order also to perform scattering, but now it's not another way to scan the reciprocal space, or to get information from the sample by using scattering of X-rays. So So starting with one of the third instruments, so starting with the ENS2, so the responsible is Lucio Martinelli. So I'm trying to give you an overview of what is possible on this instrument, but for sure, feel free to contact Lucio for any details that will be missing during this presentation. So this instrument is devoted to the analysis, to the studies of the surfaces and nanostructure that can be grown on the top of surfaces. So you have, I think it's a node schematics, but the idea is that you have something which is you can find sorry, in any MBE, any laboratory which is able to look at the ultra high vacuum. So this is a really a laboratory class instrumentation, and obviously this instrumentation is seated at the on the beamline to be used with X-rays in situ. So very clean conditions to make the growth of any kind of materials. So you have the physical route, so molecular beam epitaxy to deposit from 10 sources. You can deposit on your own what you want, more or less. And then you can make the growth of any heterostructure, thin film, or 2D or very 2D, just one layer of atoms or two layers of atoms, for instance. You can couple, and you can, at the same time, let's say, you can also use this UHV chemical vapor deposition route. So it's a chemical way. So now you can insert some gases into the chamber, and then and you can make the reaction between molecules and the surface, and then you can combine physical and chemical routes to make the growth of anything. And then you can you can now monitor during the growth. You can monitor the change of structural properties by making some scans that allows to make surface diffraction, reciprocal space map. This is the black dot are the reciprocal nodes of your system, and then with a smart way of making all this movement of the detector and the orientation of the sample, you can really map where are located the reciprocal nodes, and also you can monitor, and you can measure precisely the intensity of the nodes and what is the intensity distribution around the nodes. And you can, to a larger extent, you can get access to the morphology of your current state of your deposit. So if you have some electronic density that corresponds to an assembly of objects, and then you can follow this. You can retrieve these parameters from by performing some GISAX experiment. So typically, you are able to make the growth of that. You can, starting from a substrate, you can deposit a 2D materials, so a thin layer of graphene, for instance, in this case. And on top of that, you could also deposit some. You can make the growth of nanoparticles. So this is heterostructure. You can make the growth of nanowire. So with UHV CVD technique, and for sure you are able to monitor the growth and to check how the parameters evolve, structural parameters evolve, and then you can understand what could be you can optimize, you can improve your model. Two examples just to illustrate that you can perform such a beautiful reciprocal space map of the not so many layers on top, layers of atoms on top of a substrate, and you can have the signal from the substrate, from the different layers, and then from that you can by fitting the intensity, and you can deduce the atomic structure. You can precisely measure the distances between all the atoms by least square fitting of a model with a ROD, famous ROD analysis software. So you can solve the surface structure, and you can, as I said, you can solve as well the morphology. So what are the main distance? What are how the facets are oriented with respect to the substrate, for instance. What is the side or the size of the cluster and so on. Okay, now going to the goniometer. So multi-purposes goniometer. So this is also a diffractometer. And as I said, on this goniometer, we can perform a lot of scattering, X-ray scattering techniques. So Samuel Tardif is responsible of this instrument. So as I said, so feel free to contact Samuel directly to have more details. So basically, this instrument is able to do a lot of things, a lot of techniques. So reciprocal space map on thin sample or maybe not so thin sample. You can do some diffraction. So surface diffraction. You can, as I said, I'm going to give you more details on this X-ray reflectivity. And an asset is thanks to X-rays we can monitor by in situ experiments. Or operando experiments, you can monitor how the structural properties are changing with the external parameters, for instance. And then this instrument is more now is quite really improved and heavily used for the studies of interfaces. So we are using the higher part of energies of the bending magnet source, so starting from 20 kV up to 30 kV, for instance. And then in order to really probe inside the materials, and then in this case we can cross the top solid liquid layer in order to probe the interface between the solid and the liquid. And we are also able to cross the solid layer on the top of another solid substrate, and then to understand what are the properties, the social properties of this interface. Alors, first example, maybe yes, this instrument is really well used for reflectivity. And this is quite simple, so we can really cross this maybe dense, not so dense, clearly. And sorry, just and this technique is able to probe to obtain to retrieve the electronic density as a function of this vertical direction. And it is really, really suited for the study of surface modification, multi-layers, bonding interfaces, and confined ions. In this instrument, we're able to go towards high throughput. So ex situ experiment, in situ operando as well. So we have now we can look at a lot of number of samples. We can design, thanks to the additive manufacturing, we can look at several cells and different geometry of our samples. And at the end, at the back end, we have this data analysis workflow. So software to analyze the data. So reflectivity is quite simple. So you have such a stacking of materials with different electronic density. And by changing this angle, you measure the reflected beam, and you can measure this curve. So intensity as a function of the angle of the QZ direction. You can deduce, you can inverse, or you can deduce, or you can apply a model to fit the data in order to go to the electron density profile. And from this density profile, you can measure, you can deduce a lot of things. So for first example is to get rid of some fluor in the electrolyte for the battery technologies. So these teams have studied operando during cycling and uncycling, charging and discharging. They have been able to measure the reflectivity as a function of time and the function of the voltage, like this, or the current. And they were able to look at the formation or not of the solid electrolyte interface between the electrolyte and the electrode. And then it was a good measure to clearly reveal that this additive inhibits clearly the decomposition of the electrolyte, which was very a good information to obtain from this technique. So it was also a double operando measurement. So during the measurement of one cell, the other cell was still hedging, still working, and then the two cells were looked alternatively by reflectivity. Another example, just to mention that when you are looking at structural properties in battery materials, you have to be careful about the radiation damage. So in a polite way, we are talking about beam interaction with the experiment, with the sample, but clearly you have to make sure to get reliable data that the dose, so the quantity of the amount of energy per second you put in per kilogram or per second you put in the sample can't change the chemistry of and also the structure of your material. So in this nice paper, the colleagues have recommended to use this quantitatively, to use this kind of dose on this push shell geometry samples to avoid to have data which are not really reliable. So clearly, the idea was to decrease or to shorten the slits, but to reduce the beam intensity in order to be sure to measure something which is reliable. In this collimator, as I said, we are able to do a lot of kind of experiments. So as I said, GZAX there, and then this is a crystal truncation rod. So imagine you have this reciprocal space of your sample, and you can probe. There are two possibilities. If you are rich and you have a fast detector and you have a lot of flux, you could measure. You could do a reciprocal space map. So and then you cover any points in the reciprocal space with some scattering intensity. So it takes time, and you need to have some flux in your source. As did the old colleagues, and so it's better sometimes to go faster, just to make some radial scan in red, or a specific scan. This is a crystal truncation rod scan, in order to rapidly have the distance between the node, and to locate the node with respect to the space origin. So, and another thing we can do is to do also some kind of, you can illuminate this model system where you have such a electronic density feature. So this is I guess this is air or water. This is silicon oxide, and this is silicon. And then if you do the Fourier transform, or if you do some scattering experiment, you should obtain this kind of scattering curve, intensity as a function of the angle, and then around the Bragg peak, which corresponds to the periodicity of the constructive interferences between these layers, you can have access to the shape of your elements. So actually, you can have the size, the dimensions, and the roughness, for instance. So, and this measurement has been done at several temperatures just to look at how this pattern evolve with temperature. And then they came up to this model. The best explanation of this data is for the moment that okay, there are some silicon oxide filling the air and water region. You can also do some GISAX on this instrument to some extent. And the last instrument, and I'm more involved in this instrument, is the Lowe Max instrumentation, so which is able to do some X-ray Lowe microscopy. So this is an imaging technique, and X-ray Lowe it is scattering. So this is a combination of diffraction and imaging. So what is this technique is similar to EBSD, if you know that. So it is a technique to have a measure of the orientation on your surface. But in our case, this is easily done with a high resolution in terms of angles. So we can retrieve the orientation, the local orientation and strain in any point on your microstructure. So every half microns, let's say, you can add the orientation and the strain. So the latest parameters of the unit cell with a very, very high resolution. Thanks to the penetration of the X-rays, you can really probe under the surface. And this is very, very satisfactory because sometimes the surface is not really the first nanometers or the first micron could be degraded, but the properties are explained by the inner part of the surface. You can have an idea of the plastic defects that can happen in your materials. And clearly, it's so simple to use because you have simple to put your sample on at the center of the experiment, and then you can collect such a Lowe pattern on that. We were able to perform some complementary techniques, measurements on top of this standard way to measure the Lowe pattern. At the same time, you can make the elemental map and compare to the structural map obtained by the Lowe diffraction, and also you can have a visible picture of your so a microscopic visible picture of your sample surface. You can perform obviously some in situ and operando experiment. So talking about that, so you can heat up the sample, you can cool down the sample, you can look at the light emitted from the sample because the light is excited by the X-rays. You can stretch, you can compress, you can bend your sample on the beamline and follow in situ how the materials respond. You can perform some 3D measurements. This is the additional measurement I was talking about. And also you can do some operando. So this is an example where you during the charging or discharging of some nanoparticles, you were able to measure the strain. I'm going faster. So Lowe diffraction is different from monochromatic diffraction. So simply you have to it's in one shot you can do the reciprocal space map, but there is no free lunch. Actually, this is a particular reciprocal space map. Actually, you are making the map of the directions of the reciprocal map. So each point there, and these black points will be the spot we can see in the Lowe pattern, corresponds to a direction in the reciprocal space. Okay, and then this, I don't want to go into detail, but actually this technique, the standard way, when we measure the Lowe pattern, you have only 5 over the 6 lattice parameters because we don't know precisely the energy. We can't, for the moment, we don't determine the energy experimentally. So the length of the the distance in reciprocal space between the node and the origin. But if you add the measurement of one lowest spot energy, then you have the 6 lattice parameters. And then actually for the mechanicians, for people working in mechanics, you can have access to the stress, which is very, very valuable. So we have on the Beamline a suite of softwares to enter the data, to visualize them, visualize it, and to obtain some structural properties from it. And then we have the Laue tools and Laue-NN. Laue-NN is a software which is based on using the neural network model. So it is a classifier, and then all this software suite help the users in handle to handle the data, visualize and interpret the data. So you can download this software, you can install it, and but for sure we are using them at ESRF with HPC computing resources of ESRF, which really accelerate the data treatment. What can we obtain? So in this example, this is wafer bonding. So you stick 2 materials and you want to probe is this poly SiC changing the mechanical or the structural properties of the top layer mono single crystal SiC. And then you can analyze the data, and then this is a map of the strain with such a unit of resolution. And you can see, and the idea of this work is to correlate or not the grains which are underneath. So the grains could explain this strain variation. So you can have also statistics, a very good statistics of the strain distribution. So you have the mean value depending on so you can measure with the Laue fraction, you can measure the absolute lattice parameters. And this 0, this is a textbook value. But so we can measure this 0 value from the experiment, but we can also measure the distribution, the width of that. A second example in this case is to use so we can induce the emission of light, and then we can collect the light. And we can, using a dispersing system, a grating, with a spectrometer, we can measure the light intensity as a function of the wavelength in visible range. So this is really valuable for photonics system. And then these are, for instance, if you look at this single nanowire of emitting diode, so this is a core gallium nitride, and then on top of this core, they make the growth of the quantum well system, and in this region you have the emission of the light. And the idea is to optimize. I guess I'm not sure now, but maybe could be the light coming from this region or maybe this region. I don't remember. I'm sorry. One bond is very typical to be is very interesting to optimize, and then you can measure at the same time. You can correlate what is the level of strain in the plane, in the section of the nanowire, or in this direction, so along the z-axis, and you can measure. You can correlate the strain and the intensity of the light which is emitted, and also you can have an idea of the defects density that could explain the change of the optical properties. The last example, I guess, it is for the battery materials. So, in this electrode, they are composed of many nanoparticles of these complicated materials, and then you can, with Laue diffraction, Laue max, we can collect a lot of maybe several hundreds of nanoparticles. And for this one, for instance, you can follow as a function of time, but actually as a function of the voltage, you can follow how this particle at the end will see the change of the strain. So the C over A ratio, this is a strain along the C-axis, and you can see this is with the time. So at some moment, the strain is larger, the value, yes, the strain is changing a lot, and then at the end, the particles actually breaks into 3 parts, and then you can also follow the misorientation for all parts of this crystal, of this particle. Okay, and the last example, it is on the polycrystal, so chromium that covers the zirconium polycrystal. So you can do these orientation maps as you could do with EBSD, and but with the X-ray, you can really, with a very high resolution, you can have the strain in any region of your sample. But also, let's go back there, you can select one grain and then and see how the strain is changing inside the grain. So this is a beautiful example. This is a grain which is more or less the c-axis is pointing towards which is normal to the surface. And then so how we can interpret this the main color of these different lattice parameters or strain components. We can interpret that by a shear, so a compression along the c-axis, and a shear component, which is parallel to the rolling axis during the manufacturing. And thanks to this Lawemax microscopy, you can make the distribution. You have all the components for all the points. So maybe you have a 10,000th point of measurement, and then you can do some distribution statistics on the average level, the mean average of the strain component, and also the distribution. Okay, maybe I'm going to quit there. So you can have some depth resolve measurements simply if you do some additional measurement by making the travel of this wire, and then you can cut the intensity touching the detector, and then you can retrieve where the lowest spot comes. And actually, you can and then you can find the grain, the strain gradient inside the material. So it is a depth resolve strain map. Okay, so this is the energy measurement, and then I'm going to the conclusion. So the key message for this beamline that we are able to investigate surfaces and interfaces. So objects, nano objects, micro objects, assembly of objects, and then in order to have some reliable data, representative data. So these are the main keywords of the beamline. So if as user, if you feel that you have some needs in this particular words, so feel free to contact us. So the techniques, this is all related to scattering and diffraction with the grazing incidence. We can do some in situ and operando experiment. We can do some experiment under ultra high vacuum, and we have also this Laue diffraction microscopy. The perspectives. So in the mainstream of ESRF improvements, so we are going toward an increased automation and throughput on the different experiments and technique. So the idea is to get more representative data and most of all reliable data. So there are 3 ways to do so. So in the future, we will receive a new Laue detector, a pixel bridge detector, which is going very fast. And then also we will keep on improving the workflows, both for online and offline analysis. We are thinking about and starting to introduce some AI assistance during the data acquisition, and what is important for us to help really efficiently the users is to train them, and then we are planning to do more tutorials and practicals and obviously improve the software to be more user friendly. ever and ever. And then what is important at ESRF that the people are really committed to help the users. So on BM32, you have a skilled team in science, in instrumentation, and the data analysis. And then we are really open to custom your units to make the experiment that really can answer your questions. So this is my conclusion. So please contact us and we will be really happy to help you.
Thank you very much for that nice comprehensive talk on BM32's capabilities. We have a first question